Okay guys, so this is the first video of 4 in this first series or first part. We're going to just quickly go through this. I'm going to highlight a few important things that I think are important for you to highlight. Oh, not that color, I want blue. Okay, so we're starting Unit 6. This is covalent compounds and molecular compounds. We just got off of learning periodic trends and ionic compounds. Okay, so in Unit 5 we studied ionic compounds, which are formed through ionic bonding, the actual transfer of electrons between two atoms. Ionic bonds can be formed between several components. These are the conditions. You can either have a metal and a nonmetal, a metal with a negative polyatomic, or the ammonium ion and a nonmetal, okay? Or the ammonium ion and a negative polyatomic. So there's 4 real conditions that you're going to see when you have an ionic bond. Ionic compounds exist in a crystalline lattice structure. That was towards the end of Unit 5 notes packet, making it impossible to attain a single unit. So what this means is, for example, if you have NaCl, okay, it's formed from the Na positive ion and the Cl negative anion. When you put them together, you get a ratio of 1 to 1, okay? In a single unit, okay, or crystalline lattice, we don't just have one of each ion present solely. You have probably thousands of them, but in that ratio of 1 to 1, okay? Now, so it makes it impossible to obtain a single unit of the compound. Thus, the formula for an ionic compound simply represents the smallest ratio, okay? And remember, you have to reduce if needed. We do call ionic compounds formula units. Now we're going to kind of shift gears now and look at covalent compounds. So when 2 or more nonmetals, okay, and this is key. Earlier we looked at ionic, metal, and nonmetal, or metal and a negative ion, etc. Covalent are going to be between 2 or more nonmetals, so that upper right-hand corner of the periodic table. In ionic, we transfer electrons. In covalent, 2 or more nonmetals, the electrons are shared between them. Okay. Now, electrons are shared between the atoms since they both have high electronegativity values. If you remember the trend for electronegativity, it increases up and to the right. Okay. Hopefully those that did their project on electronegativity got it correct. But they have high electronegativity values and tend to hold their valence electrons more strongly. They share electrons then. In order to gain the stability of having 8 electrons in their outer shell, that's their main goal. They want to have 8. Greater stability is equal to lower energy. Covalently bonded atoms result in what are called molecular compounds because true molecules are formed. A molecule is the smallest unit of a molecular compound and exists as a free independent particle. So molecular compounds are given molecular formulas which identify the exact numbers and kinds of atoms in the molecule. So here's an example of a molecular formula. Okay, CO2. There's 2 nonmetals. These are covalently bonded together. In one single unit of CO2, you would have 1 carbon and 2 oxygens. Okay, and so for covalent, we can actually look at what an actual molecule of that would look like, unlike salt and NaCl, where it just shows the ratio. Okay, I'm going to kind of move down a little bit. So how do covalent bonds form? Okay, we're going to look at some energy diagrams. This is particularly important if you plan on going into AP Chem and kind of understanding what it looks like for a bond to come together between 2 atoms. So covalent bond formation. A single atom is held together by the attraction between the protons in its nucleus and its orbiting electrons. When 2 atoms approach each other, each nucleus also attracts the other atom's electrons. The sharing of valence electrons in covalent bonding is a result of both atoms fighting for the electrons, with neither one winning. Consequently, the atoms are effectively bonded together. And so here is a little diagram of what that might look like. Internuclear distance, so the farther obviously we go right, the atoms are further apart. When you go left towards the axis, the atoms get closer. And so look at the energy. Out here, okay, when atoms are far apart, they possess a certain amount of energy. When they get closer to each other, so as we start to travel this line, the two atoms are going closer and closer to each other to when they reach a certain point in which their energy is lowest. If they push together too much, okay, their energy skyrockets because they're actually starting to repel instead of attract. And so each set of atoms, now this is just a diagram, each set of atoms, whether it be 1, 2, or 3 atoms trying to bond together, will eventually get to a point where they reach the lowest energy possible, and that's it when the covalent bond forms and they sustain each other. So if the atoms get too close, and this is basically just kind of writing or reading through what I just said, if the atoms get too close, as in the example here, okay, they repel each other because of proton-proton and electron-electron repulsion. A molecule is most stable when its electrostatic potential energy is at a minimum. In other words, when its atoms are located at a distance where the proton-electron attraction balance these repulsions. At this distance, the atoms can share their valence electrons and form a covalent bond. Now, every atom bonding to another atom is going to be different in that distance. So don't pay attention and care so much about bond length. And what the actual number is. Know that every type of bond does have a bond length, though, single, double, and triple, and etc. Okay, so for this first part, I'm just going to kind of stop here, and I'm going to make 3 more videos kind of in each section so that you can review it as you need. So go on to naming and formula, writing for